So, everybody in the research community talks about latent representation. So I think a good starting point is to try to define them and to say what makes them good or bad. And I'm going to ask for your help on this one. So I'm going to show you a couple of pictures, and I hope you can answer really quickly what you see in those, because we only have 20 minutes. So, what's this magical picture? What? Cat. Cat. Cat, everybody, cat. Not those cat.
No, it's a dog. It's a dog.
Okay, where's the dog?
The small one.
The small one. Okay, that's great. So do you know how you know it's a dog?
Do we know what?
You know how, why do you know it's a dog? That's a dog and not a cat? Yes, because you have a good latent representation of what a cat and a dog is. You know about a cat that it has pointy ears, it's furry, and most of when it goes meow, it doesn't bark. So barking would be a dead giveaway that that's a dog. So, yeah. So basically, what the latent representation is, from the machine learning point of view, is nothing more than a vector of real value numbers, which tries to correlate with abstract features from the input data. Now, the more abstract the features, the better the representation. Ideally, if you have a neural network that you'll be able to look inside its mind, and whenever it saw cat, it saw something like this inside its brain, that would be awesome. That's the perfect latent representation. Well, in reality, you get something more in the lines of this, which is an abstract representation of an abstract representation. So, another important thing about abstract representations is that they have to be separable and coherent. What does that mean? So we took a little example here. It's not what Tripod does, so don't get confused. So we have digits, and we have projected BD representations from their latent state into bidimensional space. And we colored all the data belonging to the same class, so the ones are blue, the zeros are yellow, and stuff like that. This is not our data, this is not actual real data, but the idea still holds. So you have some portions of the data which are really good separable, really easy to separate. So we have the ones, the zeros, the sevens above, right? But we also have this cloud of points that overlap, which is also okay. Because, you expect to maybe confuse a 5 with a 6 or a 5 with a 3. What you don't want to happen is to have a 6 confused with a 1. And they're on opposite sides of this representation. If you have a network that actually put a 6 near a 1, it actually meant that it didn't learn anything from your data set, so you need to build something else. Now, the same idea holds for words inside sentences. So if we would again project words based on the latent representation like neural network, we would expect that words that have similar meanings or that are used in similar context to be close to each other. So this is one quick example. Now, getting back to Tripod, again I'm going to ask for your help on this one. So I chose an example. I hope you can recognize it because it was actually intended for people who did a lot of speech in the past, but I'm going to try it anyway. So, the challenge is the following. I'm thinking of a sentence, I'm going to give you a clue, and you have to guess it. So my clue is this one. Does anybody know what that sentence is?
Red fox.
Brown fox.
Brown fox, lazy dog.
Sorry?
Brown fox, lazy dog.
Brown fox, lazy dog. Okay, that's great. How do you know that?
I just read the article.
We didn't expect that.
Okay. So basically, that's not the sentence I was thinking about. So it's not the quick brown fox jumps over the lazy dog, just to be sure we are on the same page. It's something else. And I'm going to tell you a little story in order to get to what I was thinking of. So one of the co-authors on the paper, Andre actually, said that this sentence is really overrated. He heard it too many times. He sees foxes as being red, and he thinks that dogs are only lazy if they're fat. So a lazy dog is always fat. So what is my sentence?
Red fox.
Yes.
Fat dog. Fat dog.
Okay, that's awesome. That's great. And do you agree with this one? So it's red fox and fat dog? Okay, it is. It actually is. Guessed it right. Okay. So let's see what happened. The idea is that people who have seen the sentence in the past, when they saw my clue, probably would have thought about the quick brown fox jumps over the lazy dog. Now, I told you the story and I gave you some context. And you are able to say that, okay, brown is not brown, it's red. And we are talking about a lazy, a fat dog, right? So the first one was memory-based representation, that thing jolted your memory. Next, I gave you some context and you are able to replace the words. And finally, I think you can build a lot of sentences that look like this one. So we can have the quick white fox jumps over the gray dog, the quick jumpy fox jumps over the, I don't know, the old dog. Okay, that's great. So that those sentences,
The blue dog.
the blue dog, yeah, the blue dog is great. So we have a lot of sentences that have the same skeleton, and I hope you indulge me to call this style, although it's not style. I know that this is something. This is a legacy part of Tripod that comes from speech synthesis. I will get to that later on the presentation. So what is Tripod? Tripod is an open source machine learning toolkit which computes latent representations for sequences, not for individual tokens, as opposed to WordVec and other, BERT and other systems such as this one. It computes the free representations I talked about. So we have the memory-based representation, the style-based representation, and the summary or context-based representation. And to do that, it uses something called attention. And to get what attention is, I have selected two mainstream examples from machine learning today. So on the left side, we have image captioning. So you need to write what the picture is about. On the right side, we have machine translation. So this is accomplished, the one on the left, by a type of models called sequence-to-sequence models, which try to guess the output, the captioning of the image word by word. And to do that, they actually emit a token, then use something called attention over the input data, and they emit the next token. So what attention does, it allows the model to focus only on a small portion of the input. So it doesn't see the whole input, it doesn't get confused. So when it has to emit frisbee, it actually looks at the frisbee in the picture. There's a frisbee there, I don't know if you can see it. When it says dog, it looks at the dog under the bed, and so on, right? So this is Tripod. Tripod has three distinct networks. The first one, so all of them are encoder-decoder architecture, sequence-to-sequence models, and they all apply attention. Now, the strategy on which they apply attention actually dictates what the learned representations are. So the first one actually tries to, all of them have the input data, try to fuse it to a really small vector, and then try to reconstruct it word by word. Now, the first model applies attention over the input data, so it learns to focus words that don't belong or are not captured by the language model. So probably it will focus on quick and red and brown and lazy and stuff like that. It will not learn the language model instead. It will skip function words. The next representation is computed by applying attention, but this time not on the input data, but on a limited number of tokens. These tokens actually start to group together so that the model optimizes and is able to, whenever it sees sentences that look alike, it maps to the same token. So this is where you get style from. And the last one is really easy, the memory-based representation. Whenever you overfit a model, you actually get memory-based representations. So the last one was obtained by actually adding a lot of attentions over a lot of tokens. So in theory, the model could learn all sentences inside the training data by heart. Now, as I said, Tripod is open source. You can install it. It comes with the Python API. You just install it. You import the main API. You tell it what model to load. We have an English model, a Romanian model, and the JavaScript model, because that's actually what we use Tripod for. It's for detecting malicious versus non-malicious code inside the web pages. You can apply it over your data, you get the numbers, you can measure the cosine similarity between them. I have, for examples here, two sentences that relate to science and mathematics, two more that relate to administrative stuff, Bucharest, I'm not going to read it right now, government and stuff like that. So you can see we have rendered the representation on the right side. We have the overall representation is obtained by reducing the dimensions of all the representations and projecting them into dimensional space. But I'm going to speak about the other representations. So as summary, the first two sentences and the second two sentences are really close to each other because they're probably related to the same stuff. But if we look at the memory-based representations and the style-based representation, you see that sentence, the first and the last sentence are really close to each other because they are probably definitions of something. The same thing applies for code. I have a couple of examples. These are easy imagine code. We have two condition print function code sequences and another really unoptimal sorting algorithm. So the summary, again, we have the first two. So we have, let's just look at the style token and the memory-based representation. So the first examples collapse to each other, but for those representations, but not for the summary-based one because they use different variables and different conditions for the print system. Now, also have a couple of resources. So the whole code is available on the official GitHub repository. We have the quick installation package and also interactive collaboratory demo if you want to use Tripod for your own data. Thank you. Question?
There are questions, please. We have time.
How much time?
Doesn't matter.
Would you be able to use the tripod resource to measure the similarity of students' submitted homework in programming assignments?
I think so. I think that would be the first use case.
Context.
We actually evaluated Tripod by using two natural language processing Cora for textual inference, I think. So you have two sentences that you have to say they are neutral to one another, if they are contradictions, or they are indications, but I think you can train something to do text similarity between any two sentences. So yeah, that's a good use case.
Please.
Same question as before. Why LSTM?
Why?
Why LSTM?
Why LSTM? But that's just one approach. I mean, would you like to see something else there? I mean, we can do it with convolutional neural networks, of course. We can do it with any other model that can achieve sequence-to-sequence modeling, but I mean, LSTMs was the quickest and non-dirtiest way to get there, so they kind of work. I mean, the trick itself is in the attention, the style tokens, and the memory-based representation. So, I mean, those can be learned by applying any other sequence-to-sequence model and conditioning it using the same strategy.
The thing that I really don't like is this kind of words. I'm curious, what was your thinking process when you said, yeah, LSTM does fit well to this program?
So you just tried. I mean, the first thing was LSTM. Yeah.
Ah, you didn't compare this with.
No.
Aren't you interested to do it, in doing it?
Actually, I'm interested more on seeing how we can condition a single decoder and doing partition dropout on the input, so we can maybe make the representations that are learned by the model not overlap with each other, because right now we do. I mean, the style tokens and the memory-based representations somehow are forced to capture something that would be normally handled by context. And you can actually achieve that if you do something called partition dropout on the inner layers of the network.
What about the training? Resources, data training
So it was the
time, training time.
Okay, so the model for English and Romanian on trained using Wikipedia, randomly sampled Wikipedia sentences. I think we stocked up 1 million sentences or something like that. Training, it took like 1 week, and we used a single GPU for that.
Okay, so can you go back to the slide showing the vector representations? So these representations here, when you speak about the other one, the
This one?
yeah.
Yeah.
The GSD, the memory, and the summary. These are 2D representations of 4 multi-dimensional vectors, right?
Yes.
Where are these vectors within the architecture?
So they are actually the attention output that conditions the memory. So,
Okay.
So
it's the output of each attention block within each each of the three.
Yeah, but there's only one attention block. We apply attention only before we start decoding a sentence, and we repeat the same attention vector for each decoder step.
Okay. So that you don't have a single attention output for a sentence.
For a sentence, we have a single attention output then.
I don't understand.
So we have the encoder,
Okay.
and we use in order to compute the attention, we use the final states of the encoder.
Okay.
So we compute the attention, and then we have the decoder, which is always fed with ground truth data for the previous step, and it's also conditioned on the attention output.
Okay. So
And
the
it's the
attention output stays fixed.
Yes, for the entire
And
sentence.
is computing only in the encoder.
Yes.
Okay. And this is what you are projecting into the other slides.
Yeah. And for all of those, I mean, the idea is the same attention.
Okay.
Okay, thank you very much.